Hello and welcome back to the course. So today we're looking again at harmonic functions, and we're going to look at the identity and the maximum principle theorems. And this is subsection 712 in the book, and you can get the book in the linked in the description free as a PDF, or you can buy an inexpensive paperback to follow along. Okay, so what are we looking at? So let's first look at the identity theorem for harmonic functions. So remember, harmonic functions are solutions to the Laplace equations, or locally, they're the real and imaginary parts of holomorphic functions, which is really why we're interested in them because we're studying holomorphic functions. Now, you will not get an identity term in the same way that we get them for holomorphic functions. Zero sets of harmonic functions can clearly have limit points. So for example, take the simplest possible harmonic function, real part of z, right? Now, the zero set of this function, well, it's just the y-axis, right? That's wherever the real part is zero, right? So it clearly has lots and lots of limit points. But what the identity theorem will say that there can be no open subsets of the limit points. So here is the identity theorem. Suppose that we have a domain in the complex plane, and we have a harmonic function on that domain. Now, suppose that there is some non-empty open V, and f is 0 on that V, right? That's a subset of U, right? So it's the zero set contains an open subset. Then f is identical to 0. That's the identity term. So we can have limit points, but we cannot have open subsets, right? So there can be lots of zeros, but not too many. All right. And it's really, maybe I should say first, it's really, this sort of property is a property of functions that are given by power series, and we really have that harmonic functions are given by power series, a kind of a special real power series. It's not just a power series in x and y or z and z bar. It's a power series in z plus a power series in z bar, right? Because it is, at least locally, the real part of a holomorphic function. Okay, so suppose that let's name the zero set of f zf, right? And now this could be a complicated set, but let's suppose it has an interior. So basically, suppose that f is 0 on an open set. So then take z to be the closure of the interior of zf. And we want to do this in the subspace topology on U. So we want Z to still be a subset of U, right? So really, you could just take the interior of ZF, close that intersect with U, right? That's the subspace topology, right? So we have a closed subset of U, in the topology of U. And F is 0 on it, and it is the closure of the interior. All right. So suppose that Z is non-empty. If it's empty, then we're done. So suppose Z is non-empty, so pick a point P in Z. Now, if we look at, Z is a subset of U, so there's a small disk around P that's in U, right? And because Z is the closure of the interior of ZF, there has to be some open subset of this little disk that is actually inside the interior of ZF, right? So F is really 0 on some open subset of this little disk. Now, this little disk is simply connected, right? So there actually exists a holomorphic function defined on this disk such that f is the real part of this holomorphic function on that disk, right? All right, so f is holomorphic. And now, because f is 0 on some open subset of this disk, that means that h has to be purely imaginary, because the real part of h is f on some open subset of this disk, right? That means that H is, this can be proved and very simply, you could just use this CR Cauchy-Riemann equations, or maybe the open mapping theorem, or there's a bunch of ways to prove this, that it's constant on some open subset of this disk, right? H is, right? Well, we have identity for holomorphic functions, so the disk is connected. So therefore, H is constant on the entire disk. So that means that F is constant on the entire disk. Well, this, F was actually 0 somewhere on the disk, right? So if it's constant, it's actually 0 everywhere on this disk, right? So therefore, Z is open, right? Because for any point P in Z, we found a little disk that's actually inside the 0 set. So that's in the interior of ZF, right? So therefore, Z is open. But Z is also closed, right? Because, well, it's the closure, right? So it's open and closed subset of U. U is connected. Therefore, Z is equal to U, and we're done, right? Okay. Let's do the maximum principle, right? So we have the identity, maximum principle. And again, we're going to do it just by, in the same way. We're, going to use what we know from holomorphic functions, right? So suppose that we have a domain, and suppose that we have a harmonic function on this domain, and suppose f attains a local maximum or local minimum. Actually, the maximum principle is really a minimum principle for harmonic functions. For harmonic functions, and we'll say this in a proof, I mean, you can always take minus a harmonic function that's harmonic. So, minimum, maxima is the same thing. So if it attains a local maximum, then it's a constant. Right? So you don't need to take absolute values here, right? Just, if f itself, because now it's real valued, so we can talk about minima and maxima, right? Okay, so without loss of generality, as I said, just assume that it's a local maximum. So at some point P in U, F has a local maximum, right? Now, we could just basically assume that it's a global maximum, right? Because it's going to be a global maximum on some small subdisk, right? On some small disk that's contained in U around P, right? Now, again, a disk is simply connected, so therefore there exists a holomorphic function whose real part is F, right? And H takes this disk. Well, it's not quite equal to this set, but it goes into that set, right? So whatever the image is, right? All the real parts of of H of something might have to be less than f at P, because f at P was the maximum of the real part of H, right? But also, H of P is on this boundary of this set, right? Because, well, I mean, it attains the maximum there, right? F does, right? So, and that point is clearly on the boundary of X. So therefore, it's going to be on the boundary of F of the disk, meaning that F of the disk cannot be open, right? Because H of P is going to be on the boundary of it, right? So if there's a point in the boundary that's in the set is not open. All right. Well, this via the open mapping theorem says that H is constant, right? The only way that H, this disk is a domain, right? The only way for the image of H to not be open is for H to be constant. All right. So that means that, well, if H is constant, F is constant, right, on this disk. that means that f is constant on U by the identity theorem, right? All right. So we have the maximum principle. So we have identity, maximum principle, basically just applying the, like this was the main, key point in both of them, right? We look at a small disk is simply connected. There we can actually find a holomorphic function whose real part is f, right? Okay, so let's look at some useful exercises from this. So you could use, I mean, it would be circular reasoning at this point, but I mean, there are ways to prove the maximum principle. We'll see that in a bit, for harmonic functions without resorting to holomorphic functions, right? So if you would have that result, right, you could actually prove the maximum principle for holomorphic functions. So basically, the two are equivalent, right? So prove the maximum principle for holomorphic functions, the maximum modulus principle, right, via the maximum principle for harmonic functions. And the hint is to consider this guy, which is harmonic, right, if f is holomorphic. All right, so next, well, whenever we have this maximum principle, we sort of have, two versions of it, or two useful, or maybe two most useful. There's more versions of it, but maybe two most useful versions of it. So one version is, well, suppose that inside you have a maximum. So an almost equivalent state, well, this is equivalent. You can prove one from the other, right? Suppose that you have a bounded domain and a continuous function on the closure, right? Which is harmonic inside, then then f definitely achieves maximum minimum on the closure of U, right? This is a continuous function on a bounded closed set, right? On a compact set. So therefore, by the maximum principle, it has to do so on the boundary, right? So prove that from the other version of the maximum principle that we just proved. Now we also have a so-called, not so-called, but a version of open mapping theorem for harmonic functions. It's a bit simpler. It's really just the maximum principle in this case. So suppose that I have a harmonic function on a domain, then prove that f of U is either an open interval, and the open is the key point, or a single point, right? So it's continuous. It's always an interval, right? That would be just continuity. But the key point is it is an open interval, or basically f is constant, right? So then it would be a single point. All right. So that's it for today. So next time we'll start looking at the Dirichlet problem, trying to solve if we have on the boundary of a domain, we have a continuous function. We'll want a harmonic function inside with those boundary values. That's the Dirichlet problem, right? So that's what we're going to look at next time. All right. So see you then.